If you're a software engineer, you probably know the absolute magic of taking a tool built for one highly specific job, turning it completely sideways, and somehow using it to solve an entirely different problem.
Oh, yeah. It's the best feeling.
Right. So, welcome to this deep dive. Today, we're pulling from a really fascinating stack of research papers, and we're starting with a 2020 Google paper that has, honestly, one of the most audacious, like borderline heretical titles in modern machine learning.
An image is worth 16 by 16 words.
Yes, exactly. And we're also going to look at some of the subsequent breakthroughs from Facebook AI and OpenAI to see how this single idea just, well, how it evolved.
Yeah, I mean, it's a title that perfectly captures a turning point. It really upended the status quo in AI research and, completely redefined what a single architecture could actually accomplish.
Absolutely. So for you listening, whether you're actively building ML models right now or just trying to keep pace with the architecture that's shaping our industry, our mission today is to give you a masterclass in architectural trade-offs. We're going to explore how the Vision Transformer, or VIT, took the exact same underlying architecture designed for processing sequences of text, so like the transformer blocks powering GPT and BERT, and applied it directly to raw photographs, X-rays, satellite imagery.
With no specialized vision modules at all.
Right. Just treating an image exactly like a sentence.
And to really appreciate the magnitude of that leap, we have to look at the landscape it was trying to conquer. Because before 2020, computer vision was ruled by a single heavyweight champion.
The convolutional neural network, CNNs.
Exactly. They had this 8-year reign of absolute dominance. It basically started when AlexNet crushed the ImageNet competition back in 2012.
Right, and from 2012 to 2020, every major advance, like VGG, ResNet, EfficientNet, they were all just variations on that CNN theme.
Yeah.
And the core assumption of a CNN is, frankly, highly intuitive. It assumes that images have an inherent spatial structure, like pixels that are right next to each other usually belong to the same thing.
Which makes sense. A cat's ear is literally just a cluster of dark and light pixels grouped tightly together.
Exactly.
And that assumption is baked right into the architecture. So a CNN examines an image very much like a detective using a magnifying glass.
Okay, a detective. I like that.
Yeah, it scans methodically, layer by layer. The first layers look through a tiny lens, just spotting, edges, sharp color changes, maybe a basic texture.
Right.
Then the next layers take those tiny observations and combine them into slightly larger abstract concepts, like an eye or a tire.
And then the final layers combine those into the full face or the car.
Exactly. They use convolutional filters, which are these small sliding windows, to physically enforce that local spatial relationship at every single step of the computation.
And see, this is where I have to push back on the premise of the VIT paper. Because as an engineer, encoding spatial structure into a vision model seems like an absolute undeniable win.
It's a massive advantage.
Right. It is a perfectly rational inductive bias. So why on earth would researchers look at that and say, let's throw away the magnifying glass, let's throw away the sliding windows, let's just use a text transformer?
Well, they wanted to see if the transformer's core mechanism, self-attention, was general enough to figure out those spatial rules entirely on its own.
Without us hard-coding the training wheels.
Exactly. So they proposed a pretty radical departure. Instead of scanning individual pixels with a sliding window, VIT takes a standard 224 by 224 pixel image and chops it up into a grid.
A 14 by 14 grid, right?
Specifically a 14 by 14 grid.
Okay, so doing the math on that in my head, that gives us 196 separate patches.
Yeah, 196 patches where each patch is 16 by 16 pixels. And they take each of those individual patches and just flatten them out.
Flatten them out.
Yeah, so a 16 by 16 patch with 3 color channels, red, green, blue, that becomes a single vector of 768 numbers. And then they map those 768 numbers into the transformer's embedding space.
Okay, I want to make sure we're totally clear on that step, because when you say mapping into the embedding space, you basically mean translating the raw pixel data into the mathematical language that the transformer already understands.
That's a really great way to put it. The model expects tokens of a certain mathematical shape. By flattening the patch and projecting it, the image isn't really an image anymore.
It's just math.
Right, it's just a short sequence of 196 tokens. Yeah. And that is well within a text transformer's comfort zone. It's the exact same shape as a paragraph of text.
Wow.
The architecture that was designed to predict the next word in a sentence is now just processing visual patches.
Hold on, let me make sure I have this right. If you chop an image up into 196 isolated patches and just hand them to a transformer, like a stack of flashcards, you're destroying the spatial relationship.
You are.
So how does the model not just see a completely scrambled jigsaw puzzle? Like, if I hand you 196 puzzle pieces, you have no idea which one was the top left corner and which was the bottom right.
Yeah, you've hit on the critical hurdle there. They solve the scrambled puzzle problem using learnable position embeddings. In language models, position embeddings tell the transformer that, say, dog is the third word in the sentence, not the 10th. In VIT, they add specific position data to each of the 196 patches, so the model has some context of where it originally lived.
But wait, you call them learnable position embeddings. Does that mean we aren't just giving it a rigid 2D coordinate system, like an X and Y axis?
No, we give it initial embeddings, but
Oh.
the model actually updates and refines them during training. It discovers on its own what spatial relationships actually matter.
That's wild.
It is. When you crack open a trained VIT and look at its internal position embeddings, you see that the model independently figures out that patches near each other have similar embeddings.
Oh, wow.
It's like a person who was born blind learning to navigate a room by sound. Yeah.
Oh.
They eventually construct a perfect spatial map without ever having seen the physical layout. The spatial structure emerges purely from the data.
That is incredible. It builds its own internal geometry.
Exactly.
And then, okay, to actually make a prediction, does it output a sequence of image patches?
No, to make the final prediction, it uses something borrowed straight from BERT, the CLS, or classification token.
Right, the CLS token.
Yeah, this is an extra specialized token that's appended to the sequence. It
Yeah.
doesn't represent any specific image patch. Instead, as the transformer processes the sequence layer by layer, this token's job is basically to act as a sponge.
A sponge.
Yeah, it aggregates information from all 196 patches into one final summary. And that single token is what gets handed to the final classification head to say, this is a photo of a golden retriever.
Okay, but as an engineer looking at this, my alarm bells are ringing regarding the math.
Oh, the computational cost.
Yeah, because the defining feature of a transformer is the self-attention mechanism, where every token talks to every other token.
Right.
But the computational complexity of self-attention is quadratic. It's big O of n squared. So if you double the number of tokens, you quadruple the processing time. If you tried to feed a transformer 50,000 individual pixels, 50,000 squared operations per attention head per layer,
Yeah.
the compute goes to the moon, your GPU would literally melt.
It absolutely would.
Yeah.
And that melting GPU scenario is exactly why the 16 by 16 patches are so vital.
Okay.
It is a necessary engineering compromise. By grouping pixels into 196 patches, you keep n small enough for an O of n squared operation to be workable while still giving the model enough granularity to actually understand the image.
Which brings up a massive aha moment for how this model actually sees compared to a CNN.
Yeah.
Because if a CNN is a detective looking through a drinking straw, only seeing a tiny cluster of pixels and slowly building up context over dozens of layers, the vision transformer is basically looking at the whole page at once.
Yes, the eagle's eye view.
Right. Because of that global self-attention, every patch can interact with every other patch from layer 1. If there's a face in patch number 2 and a building in patch 190, they communicate instantly.
And that global context is incredibly powerful.
Mm-hmm.
The model isn't waiting for layer 50 to realize the face and the building are in the same photo. It has a holistic view from the very first operation.
So it's a brilliant hack. It bypasses the spatial constraints, it builds its own map, and it looks at the whole picture instantly.
Exactly.
But let's look at the results. When Google first trained this on ImageNet, which has, something like 1.3 million labeled images?
Yeah, about 1.3 million.
How did it actually perform against the best CNNs of the time?
It lost.
Wait, it lost?
It completely underperformed the state-of-the-art CNNs.
Oh, man. I imagine the CNN loyalists felt pretty vindicated by that.
Oh, they absolutely did. And honestly, mathematically, it makes perfect sense why VIT struggled on that data set.
Why?
Because CNNs have those built-in spatial biases, the sliding windows. Those inductive biases act like training wheels. VIT had no training wheels. They had to learn everything about how light, shapes, and physical objects work entirely from scratch. And 1.3 million images simply wasn't enough data for it to figure out the complex rules of the visual world on its own.
It reminds me of the classic analogy of two students learning to play chess.
Oh, I like this one.
Yeah, so one student is given a book of heuristics. Control the center of the board, develop your pieces early, castle your king. That student represents the CNN. They're going to win their first 50 games easily because they have these human-engineered shortcuts.
Right, they know what to look for.
Exactly. But the other student representing VIT, is given no strategies at all. They are just told the rules of how the pieces move and they have to play. If they only play 100 games, the heuristic student crushes them.
Well, what if they play 100 million games?
Exactly.
The chess analogy is the perfect lens for what researchers call the bitter lesson of artificial intelligence. It's a concept coined by researcher Rich Sutton.
The bitter lesson.
Yeah, and the bitter lesson states that human-designed heuristics and biases are helpful shortcuts when data is scarce. But eventually, those same shortcuts become artificial ceilings.
Okay.
If you give a sufficiently general architecture, massive amounts of compute and massive amounts of data, you will eventually discover internal representations that are far superior to anything a human could ever handcode.
So 1.3 million images just wasn't enough. How much data did it actually take for the VIT chess student to finally beat the CNN chess student?
Google scaled up the training to their internal JFT 300M dataset.
300 million.
That is 300 million labeled images. And when they did that, VIT completely woke up. It shattered the ceiling and crushed the state-of-the-art CNNs across the board.
Okay, and this is but if the bitter lesson means we need 300 million labeled images and a Google-sized server farm just to get this architecture to work, I mean, that effectively locks out 99% of the software engineering world.
It does.
Everyday developers don't have access to that. So how did a solo engineer or a smaller startup actually get to use this? How did it become practical?
Well, the democratization of the vision transformer came a few months later, in late 2020, from Facebook AI Research. They published a paper on DET.
DE8.
Yeah, data-efficient image transformers. They figured out how to solve the data hunger problem on a single machine using just the standard 1.3 million images from ImageNet.
See, I want to dig into the mechanisms here because the engineering tricks DET used are just brilliant. How did they force the transformer to learn without needing 300 million examples?
They essentially artificially inflated the dataset using incredibly aggressive data augmentation.
Like what?
Things like rand augment, where you're rapidly and randomly rotating, cropping, and color shifting the images during training. They use random erasing, literally blanking out random chunks of the image. And crucially, they used a technique called cut mix.
Wait, cut mix is where you splice the head of a dog onto the body of a car, right?
Yes, exactly.
That sounds crazy.
It does, but the reason you do that is to forcefully break the model's bad habit of relying on local context.
Oh, I see.
If the model is being lazy and just looking for fur textures to identify a dog, splicing that fur onto a car forces the model to look at the global structure. You are denying it the easy answers.
Right.
Instead of seeing one image once, the model sees thousands of warped, mutated variations, forcing it to learn deep, robust patterns rather than just memorizing specific pixels.
They also introduced a distillation token, didn't they?
Yes, and this is a beautiful piece of engineering. They added a new token right alongside that CLS token we talked about earlier.
Okay.
But this distillation token had a very specific job. It was trained to mimic the outputs of a highly optimized, pre-trained CNN teacher model.
Ah, so it gets hints from the CNN.
Yes.
Going back to our chess analogy, it's like the no heuristic student getting occasional advice from the heuristic student while they play. The transformer gets the benefit of the CNN's spatial awareness as a learning signal, but it doesn't permanently hard-code those sliding windows into its own architecture. It remains a pure transformer.
That is exactly the right way to think about it. But, DET was really just the first step in making VDTs practical. The real paradigm shift for data efficiency came in 2021 with MAE.
Masked autoencoders.
Right. This brought the magic of self-supervised learning to computer vision.
And self-supervised learning is how text models like BERT were trained.
Exactly.
You take a sentence, mask out 15% of the words, and force the model to guess what's missing. You don't need human labels because the data itself provides the answer key.
Yeah.
But MAE did this for images. And from what I read, they took an image, chopped it into patches, and masked out a staggering 75% of the image.
75%, yeah.
Yeah.
They handed the transformer encoder just 25% of the visible patches and said, reconstruct the rest of the image.
Wait, why on earth can you aggressively mask 75% of an image when text models fall apart if you mask more than 15%? Like, if you mask 75% of a sentence, you just have a couple of prepositions left. There's no context to rebuild from.
Well, it comes down to the fundamental difference between visual data and language data. Visual data has massive redundancy.
Redundancy.
Yeah. If you see a tiny patch of blue sky, you can easily deduce that the neighboring 5 patches are probably also blue sky. If you see half a dog's face, the other half is a mirror image. Pixels carry way less individual information density than words do.
Oh, that makes total sense. But the act of forcing it to reconstruct the image, what is that actually teaching the model?
That is the genius of MAE.
Hmm.
To reconstruct 75% of a missing image, the model can't just guess blindly. It is forced to learn the underlying physics of reality. It
Wow.
has to learn how lighting casts shadows across different shapes. It has to learn the structural symmetry of biological faces. It has to understand depth and occlusion.
Right.
By the time it finishes this self-supervised task on millions of raw, unlabeled internet images, it has a profound foundational understanding of the visual world.
And there's a computational elegance here too, right? Because self-attention is quadratic, running the encoder on only the 25% visible patches makes training incredibly fast.
Oh, it makes pre-training 4 times faster. You can unleash it on billions of unlabeled images from the internet to learn those deep structural representations, and then you only need a tiny, tiny data set of labeled images to fine-tune it for your specific task.
Like identifying a rare manufacturing defect or something?
Exactly.
Man, this paints a pretty incredible picture. We have an architecture originally built for text. We proved it can process raw images, learn spatial rules entirely from scratch, and train efficiently on massive amounts of unlabeled data without melting our hardware.
It's quite the resume.
It really is. So the logical next step, the absolute holy grail for engineers, is crossing the streams, making a model that understands images and text together.
And that brings us to a massive leap forward. OpenAI's CLIP in 2021.
Contrastive language image pre-training.
Yes, this was the moment the bridge between vision and language was finally built.
And I'm struggling to see how you cross that bridge mathematically. You have an image encoder processing patches and a text encoder processing words. How do you get them to talk to each other if they don't share the same foundational data?
Well, they train them using 400 million image-text pairs scraped from the internet.
Okay.
So imagine a photo of a dog, and the alt text, a brown dog playing in the grass. They fed the image into the vision encoder, and the text into the language encoder. But they didn't try to make the vision model predict the exact words. Instead, they used contrastive learning.
What does that mean in practice?
For any given batch of images and texts, the models had to calculate the mathematical distance between their outputs. The training objective was to push the representations of the matching image and text closer together in a shared mathematical space, while pushing all the mismatched pairs further apart.
So they're learning a shared embedding space.
Exactly.
It's like having an English speaker and a Chinese speaker who don't know a single word of each other's languages, but they are walking through a room together pointing at the same objects. Oh, I love that.
Yeah, and over time, they map their completely different sensory inputs to the exact same conceptual point in their brains.
That is a brilliant way to visualize it. And because they share that embedding space, CLAP unlocked something called zero-shot classification.
Which is huge.
Massive. Before CLAP, if you wanted a model to classify dog breeds, you had to curate thousands of labeled images for every single breed and train a brand new classification head.
Right, which takes forever.
With CLAP, you just type a photo of a German Shepherd. The text encoder projects that sentence into a specific coordinate in the embedding space. If you hand the image encoder a picture of a German Shepherd, it projects the image into the exact same coordinates.
It finds the match without ever being explicitly trained on a discrete German Shepherd category.
Exactly.
This is huge for the listeners out there building software. I mean, this unification changes the entire development paradigm. Improvements in natural language processing now directly upgrade computer vision tasks.
They feed into each other. And we are seeing incredible real-world applications of this global attention. Think about medical imaging. A vision transformer can look at a whole X-ray and capture the global context instantly.
Right, just like a human radiologist looks at the whole chest cavity, not just an isolated 2-inch square.
Exactly. Or in autonomous driving, a VIT can immediately connect a distant red traffic light 50 meters down the road with the brake lights of the car 5 feet in front of it. It sees the whole scene.
The unification vision has really become a reality.
Yeah.
We no longer have entirely separate, isolated silos where the computer vision researchers build CNNs over here and the natural language researchers build sequence models over there.
We have a universal architecture bridging the gap.
We do, though it is worth noting for the engineers that the modern reality in production is often hybrid.
Wait, really? So we didn't completely throw away the CNNs. The magnifying glass still has a use.
Oh, it definitely does. The most efficient models today often use a few early convolutional layers to handle the high-resolution local feature extraction,
Oh, interesting.
because convolutions are incredibly computationally efficient at doing that at the granular pixel level. Then, they pass those processed, slightly abstracted features into transformer layers for the high-level global reasoning. It's really the best of both worlds.
So you use the magnifying glass just long enough to make the puzzle pieces manageable, and then you use the eagle eye of the transformer to understand the whole map.
Exactly. It's a testament to the power of general architectures, but it also brings us full circle back to the bitter lesson. The underlying truth here is that massive data and massive compute applied to a general architecture will always eventually beat human-engineered heuristics.
It makes you wonder, though.
About what?
Well, we've built this universal architecture that relies heavily on eating hundreds of millions, if not billions, of human-labeled images and human-written text. But we are rapidly running out of high-quality internet data. So if the Transformer's only real superpower is scaling with data, what happens when it runs out of human reality to consume? Will this architecture hit a hard, insurmountable wall, or will it just start dreaming up its own synthetically generated worlds to learn from?
That's the billion-dollar question.
Something to mull over. Until next time, keep diving deep.